Sauce here. This is a video lesson on L'Hopitals rule. Let's take a look at a limit that we have worked with in the past. The limit as x approaches 0 of the rational function sine x divided by x. This is a finite limit. I'm going to attempt it by substituting in the value that's being approached into the expression. When I do, the sine of 0 is 0, and we're dividing by 0. This is not the limit, 0 over 0. So I can't say that it's equal. I'm going to say it's approaching the form 0 over 0. And previously, we learned to call this indeterminate, IND for short, because we're not sure whether the limit is something over itself and therefore 1, or 0 because the numerator is 0, or undefined because the denominator is 0. Can't be determined. We need another way to justify taking this limit. In the past, we used justifications of looking at the graph, which is informal. We used a squeeze theorem or squeeze principle to conceptually understand what the limit must be. We know that the limit of as x approaches 0 of sine x over x is 1, but we haven't formally justified or gone through a formal solution process in taking this limit. We can with L'Hopitals rule, which states this: if and only if a limit is indeterminate, then the limit as x approaches a of a rational function f of x over g of x is equal to the limit as x approaches a of a rational function, the derivative of the numerator divided by the derivative of the denominator. So we can use this conversion, but only if our previous attempt to take the limit is shown to be indeterminate. This is a very useful and elegant solution process for limits that are indeterminate, and it's called L'Hopitals rule. Let's use it. Taking this limit, we discovered that it was indeterminate, so L'Hopitals rule applies. We can reattempt the limit by converting it. Same limit statement, but now the expression is going to be formed from the derivative of the numerator, which is cosine, divided by the derivative of the denominator, which is 1. I'm going to reattempt the limit, substituting in 0 into my expression. The cosine of 0 is 1. 1 doesn't change. This is non-problematic, so the limit, taking the limit was successful, and of course this simplifies to 1, which we expected it to be. But we used L'Hopitals rule to get there, and that is sufficient for formal justification. Let's see it again. What is the limit as x approaches infinity of 2x squared divided by x cubed? I'm first going to try to attempt the limit. When I do, I substitute in, well, infinity is not a value, so I'm going to think of 2x squared growing, and we know that the numerator is going to grow to infinity. The denominator is also going to grow to infinity. And we're not equal to infinity over infinity. We're approaching, and the limit hasn't been taken because it's indeterminate. Previously, we had the concept of dominance, so we understand that the denominator is going to grow at a much higher rate because a cube dominates the growth of a square. such that the denominator's growth to infinity will overwhelm the numerator, and this can conceptually be reduced to 1 divided by infinity, so we know that we expect the limit to be 0. Denominator dominating. But dominance is not a formal justification, though it's very handy in helping us with infinite limits. The other thing that we can do to formally justify is algebraically we can cancel out the common factor of x squared. So we'll be reduced to 2 divided by x. And by a limit law, which is formal, we can also see that the limit as x goes to infinity when x is in the denominator will be 0. So we expect this to be 0. Let's use L'Hopital's rule to get there. It's indeterminate form, so I can convert the limit, same approach statement, but the new expression will be the derivative of the numerator, in this case 4x, divided by the derivative of the denominator 3x squared. Reattempting the limit, I can see that I'll get infinity over infinity again. So the limit has not been taken, it's still indeterminate, which is okay. I can use L'Hopital's rule a second time. So I'm going to take this expression, use L'Hopital's rule to convert it into another expression based on the derivative of the numerator divided by the derivative of the denominator, and reattempt the limit. I want to show that this expression is the same as the constant 4/6 times 1 over x. And when I reattempt the limit, in this case, I have the limit law, the limit as x approaches infinity of 1 over x. We can use the limit law and know that to be 0. And finally, the limit has been taken. It's not indeterminate. We've finished, and we've also confirmed what we expected. In this example, I used L'Hopital's rule 2 times. We can continue to use L'Hopital's rule indefinitely as long as the use is on an indeterminate form. Let's provide one more example. What is the limit as x approaches 0 of x squared times the cosecant of x? If I attempt the limit, I'm going to substitute 0 in. 0 substituted into x squared is 0. The cosecant of 0 is the same thing. If we recall, cosecant is the reciprocal of sine. So the cosecant of 0 is the same thing as 1 divided by the sine of 0. The sine of 0 is 0. And so as x approaches 0, cosecant of x approaches infinity. That's 1 divided by 0 is approaching infinity. We have not determined the limit. The limit is 0 times infinity, which is also indeterminate. This is an indeterminate form because it can be converted into one of our 2 indeterminate forms, 0 over 0 or infinity over infinity. So I want to show you that the limit as x approaches 0, this expression here is equivalent to x squared divided by the sine of x, because cosine is the reciprocal, cosecant x is the reciprocal of sine x. These expressions are the same, but now when I substitute 0 in, I can see that I get the familiar indeterminate form. So I can use L'Hopital's rule and reattempt the limit. Is the limit as x approaches 0 of the derivative of x squared, which is 2x, divided by the derivative of sine, which is cosine. And when I reattempt the limit, I substitute in and I get 0 in the numerator. The cosine of 0 is 1, which is not problematic. So the limit was successfully taken, and this can simplify to 0.